So this first page here is an introduction to what are called logarithms. And it says, what are logarithms and how are they evaluated? So in order to understand logarithms, this one first says to solve 2 to the x is equal to 8. Basically, it's saying 2 to what power equals 8? Well, over here it says division is the inverse operation of multiplication. So with 2x equals 8, by the way, this is not the same equation over here. I just want to make that clear. If this was multiplication and not exponential, and it was 2x equals 8 over here and not 2 to the x equals 8 over here, we could just divide both sides by 2 and get x equals 4, right? But because that is not multiplication, it is exponential. Listen up, guys. 2 to the x equals 8 is exponential, is an exponentiation, is what it says. To solve this, you need an inverse operation that answers the question, to what exponent can you raise the base of 2 in order to get 8? Which is the xth root, right? That's what we were talking about. So a logarithm was, this notation was created to solve for like an xth root of something. So it's written in a particular way. It looks kind of funny, but logarithm simply means the inverse of exponentiation, of an exponent. So right here, a logarithm is an inverse of an exponentiation. It's calculating the xth root, but doing it in a way that makes it end up looking more like a regular equation. So in order to solve the equation 2 to the x equals 8, you can write log 2 8 equals x. That's not what you would say, but over here, this is read as logarithm of base 2 of 8 or log base 2 of 8. Now, a base value, if you think about exponents, exponents have a base value and an index. So if you have an exponent, so I'm just going to write this on the off to the side here, exponent. Let's just use what we've been using. We'll use b and we'll use x. B has been a growth factor or a decay factor, but in terms of the name of it in an exponent, b is the base value. And then x is the index. Okay, so an exponent is made up of 2 things, a base value and an index. And so anytime you're saying like log base 2, that's what we call subscript, by the way. That's not next to the log. It's like slightly smaller and down to the right a little bit. Log base 2 of 8 is equal to x. It's basically rewriting this and mixing it up into a slightly different order. But what it ends up doing is it writes an equation equal to x. And now x is by itself. So it's rearranging using logarithm, which is the inverse of an exponentiation, and it writes it equal to x. So, hey guys, listen up, please. Thanks. So to what exponent does 2 need to be raised in order to equal 8? The answer is 3, because 2 to the third power is 8. So that's a pretty simple example. 2 times 2 times 2 is 8. So you don't necessarily need to use a logarithm to solve this one, right? 2 to what power is equal to 8? The answer is 3. The cube root of 8 is 2, right? 2 to the third power is 8. But today we're saying log base 2 of 8 is equal to 3. So the way that we're going to write this right here, it says the logarithm base b of x is defined as follows. So using the same b of x that we had before, the base value is always the subscript value here. And we call that subscript once again because that is not written next to where it says log or logarithm. It is a little bit smaller and it's down to the right. It's like when you have 2 x values on a graph. You got x with a little 1 and then x with a little 2. X sub 1, x sub 2, it's the same notation. Log base x equals y. If and only if b to the power of y equals x. B has to be greater than 0. B cannot equal 1. X needs to be greater than 0. These are the same stipulations that we had a couple of days ago when we were using our exponential models, right? Same kind of thing we were dealing with 2 days ago when we talked about exponential models. That base value cannot be negative, and it cannot equal 1, because if it equals 1, then it's just a repeated multiplication of 1, which means it's going to be equal to itself. And then x needs to be greater than 0, so the exponent needs to be greater than 0 as well. The logarithmic function y equals log base b of x is the inverse of the exponential function y equals b to the x power. So if we were to do a little bit of highlighting here, we could just kind of rearrange this and say, all right, if y is, let's say y is blue here, y is blue here. We've got x here and x here. And then the base value would be green here and green here. So those functions are inverses of one another. We talked about inverse functions already. So if you were to basically swap out x with y here, and then solve for y, you'd get that, if you're to rewrite it as a logarithm. But what we're going to be doing today is we're not going to be looking too much at functions today. We're going to be looking at simplifying and maybe solving a couple simple equations. So down here, we have the logarithmic form of y equals 8 to the x. We're going to write the logarithmic form of y equals 8 to the x power. So I want you to see if you can figure out what to do with that. Think about rearranging what we just did up top a little bit. So it's going to be rewritten, by the way, it's going to be rewritten like we did here. We're not worrying about inverse functions right now. We're just rewriting this as a logarithm equation, not an inverse. So think of it like this first example here. So I'm just going to put that example off to the side here. 2 to the x equals 8. And log base 2 of 8 equals x. So use that as your guide for this one here. What do we think it is? Log base 8 of y equals x. Good. Because the base value, again, the base value here is 8. The number that has the exponent, or the thing that has the exponent, it could be a variable, is always going to be what comes after log. The exponent is going to be the thing that it's equal to on the opposite side when you rewrite it as a logarithm. So this is going to be our answer using that same structure that we did before. So right now we're just learning how to write these. We are going to do math with them, but right now we're just converting them from exponential form into logarithmic form. Which again, logarithm is an inverse operation to an exponential. So we're just rewriting it to be able to solve for the variable in a slightly different way than you normally think about. So down here, any questions here before we move on? You can follow this pattern and use it here. That's basically what we're doing. Follow that pattern, use it here. So down here, exponential form shows that a base raised to an exponent equals the result a to the b power is equal to c. So if you have a base value, a raised to an exponent here is the answer to that equation there. And when you raise a certain number to an exponent, you get the expanded form of that, or the simplification, or the power, or whatever you want to call it. You end up with c right here. So when written in logarithmic form, The number that was the result of the exponential equation is often called the argument. So in this case, C would be considered the argument. And it says it's often called that. If you hear to referring something as the argument, it's just the value after the base of the log. So this would be log base 2 with an argument of 8 is equal to x. Meaning 2 raised to what power equals 8? Or in this case, 8 raised to what power equals x? So if you want to use highlighters or whatever it is, the rearranging of those things can be seen like this. All right. How are we doing so far? Decent? We're just rearranging stuff right now. Okay. Moving on from there, it just asks you to rewrite this particular solved equation. This is already solved for. 3 to the 4th power is 81. 3 times 3 times 3 times 3. It's got everything filled in. It just wants you to rewrite it as a logarithm, as opposed to an exponential equation. Do that with A and B. So you're going from exponential to logarithmic, and then you're going logarithmic to exponential for part B. We have the base, the index, and the argument for A, and we have the base, the argument, and the index for B in that order. So who thinks they've got A? Log base 3 with an argument of 81 is equal to 4. Nice. Any questions on that one? Okay. How can we rewrite this logarithmic in exponential? Somebody else. 10 cubed equals 1,000. Nice. There you go. So you can think of this written like 10 raised to a certain power is equal to 1,000, and that power is 3. All right, A and B down here. Do both of those. A couple more. Same process. Here we go for A and B. Go ahead and check those. Personally, I feel like it's a little bit easier to go from logarithmic to exponential form because as long as you know what the base is, you can kind of work out what the other two numbers are supposed to be, right? 4 to the power of 16 is not 2, but 4 squared is 16. So then you can just write 4 squared equals 16, if you know what all three numbers are. And then just making sure that your base value is always right after the logarithmic function. The answer in a logarithmic expression is always going to be equal to the answer of the exponential, and then the index value is what is equal to over here. Yeah, go for it. Any questions on A or B? Cool. All right, let's keep going. So now we're going to be taking a look at solving some of these. So if you have log base 5 of an argument of 125, that means you're trying to figure out 5 to what power equals 125. So it says think 5 raised to what power equals 125. What is the answer? 3. Yeah, the answer is 3. So 3. For B, here's an interesting question. -2, good. Why is it -2? What's that? Yeah, because when you raise a power, when you apply a negative exponent, what does that mean? What's that? It means division, yeah. Because exponents, positive exponents are repeated multiplication. Therefore, negative exponents are repeated division. Right? So if you're growing something exponentially by multiplying up, that means the exponents are positive. If you are decreasing a value or decreasing a value, this actually increases it because it started as a fraction. But if you are decreasing a value using exponents, it's going to be a negative exponent because that represents repeated division. So basically, you're trying to figure out what number can you apply an exponent to 4 to make it equal 16? The answer is 2, but it also needs to be the reciprocal of that, which means it needs to be divided by 16 as opposed to, or not divided by 16, but divided twice by 4 in order to make that happen, which would make it 16. So it's -2. 1/4 squared would be 1/16, which means 1/4 to the -2 would take the reciprocal of that and turn it into positive 16. This is stuff that you did back in Algebra 1, by the way, in terms of like thinking through positive and negative exponents. What about this one? What's that? Yeah, C. Why not?
Because if you get a power of 0.
Yeah. So positive exponent would be 3, 9, 27, 81, right? Negative exponent would be 1/3, 1/9, 1/27, etc. 0, exponent of 0 means you're dividing this number by itself, which equals 1. You can't raise a number to an exponent to make it equal 0. So you could say no solution, or you could write undefined, which is what I'm going to write. If you think it was 0, check it on your calculator. If you take 3 to the 0 power, it's not 0, it's 1. Because if you take away an exponent, that means you are decreasing it by a factor of the base, which means you're dividing it by the base. So if 3 squared is 9, and 3 to the first is 3, that's 3 divided by 3. 3 to the 0 power is another divided by 3. 3 divided by 3 is 1, so anything to the 0 power is 1 because you're dividing something by itself. How about this next one? I think this one might be the easiest one. Same base value. We need the same exponent. What's it got to be? 8. Yeah. It's one of the ones that's like, it seems so obvious that you question yourself. Like, is that? But is it? Yeah, it is. And by the way, look at the notation. Like here, take a look at that real quick. That looks kind of crazy, doesn't it? Log base 2 of 2 to the 8th power. Like that seems pretty challenging, but if you rewrite it in exponential form, it's basically saying 2 to the what power equals 2 to the 8th. And that would be 2 to the 8th power equals 2 to the 8th. So it's just 8. So you will see things with exponents in arguments. That will happen. And it doesn't need to be scary. It just means that that's what this equals to when taken to a certain power. 2 to what power equals 2 to the 8th? 2 to the 8th power equals 2 to the 8th power. All right. Let's continue. So let's go ahead and try to work these out here. So what is the value of each logarithmic expression? So log base 3 with an argument of 1 over 81 means that we are trying to figure out what are we taking 3 is being raised to what power to equal 1 over 81. That's what we're trying to figure out here. So my suggestion here, just try to figure out what is 3 to the what power equals 81. Don't worry about the fraction right now. 3 raised to what power is 81? Times, yes, but exponent, no. Let's just think about this for a second, though. Like, forget about the fraction right now. Just look at the 81. 3 to what power equals 81? 3 to the 4th power, right? 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th power is 81. So 3 to the what power equals 1 over 81? -4, yeah. Because -4 creates the fraction. It doesn't create a negative number. Negative exponents do not make negative numbers. Negative exponents make fractions. It means division. For B, 7 to what power equals -7? What are we saying for that one? Okay.
Because it just said it itself.
Yeah, negative exponents don't make negative numbers. So it's not going to work. Actually, we could actually figure this out we can type this into our calculators as well. Let's go and do that real quick, because you can use your calculators for these. There is a way to type in, by the way, if all you do is type in log, that's not going to work. I'll tell you why in a little bit, but that's not going to work. What you need to do if you want to actually include a base value with that log and not just have it say log, because there's nowhere to put in a base value down there. Again, I'll explain that in a few minutes, but go to your math menu. And then I think it's in this one right here. Yeah, so if you scroll down to the bottom of the main math menu and you go to letter A, it says log base. That allows you to type in a base and an argument. So if you type in log base 7 with an argument of -7, there it is, error, non-real answers. And that's because if you start off here and you're trying to get an answer that's the same number but negative, you can't you cannot raise a number to an exponent to have it equal its opposite. That doesn't work. You can multiply it by -1 to do that, or you can divide it by -1 to do that, but you can't raise it to an exponent to do that. Now you could, if you wanted to, if this was -343, then this would have an answer. I think. Well, no, it wouldn't actually. Sorry, that wouldn't work either. If this was -7 and that was -343, then it would. But yeah, undefined. Undefined. All right, C. This is another one that should be very easy. 9, yeah. Because we're saying 5 to what power equals 5 to the 9th power? Well, it's got to be 9. There's no other way around that. It has to be 9. X equals 9. Okay. So the next thing we're going to talk about are common logarithms and natural logarithms. Whenever you type in just the button over here that says log, that's what's known as a common logarithm. And it is a common logarithm because in science, what is the most common factor that you use in science? Like base factor, like in the warm-up today? 10, right? Science uses the metric system for the most part, right? Everything in the metric system is based on increments of or factors of 10. everything. Degrees, lengths, weights, magnitudes, everything in the metric system is based on 10. There are a few countries in the world that don't use the metric system more prevalently. We are one of them. England is another one. They do a mix and match though. But they still use miles per hour instead of kilometers. But Canada uses kilometers, which is all factors of 10. Logically, it makes more sense. We're just so used to using what we use that we don't really adjust for that. So apparently they tried to force it over in the 1970s in the United States, but it didn't stick and people were just like, oh, I need my irregular measurements. So we stuck with them. There's a great Saturday Night Live skit. I don't know, you might have seen it in your science classes where it was Nate Bargatze and he was George Washington and he was talking about, yeah, you see that one? Yeah, it was amazing. Just kind of pointing out the absurdity of the number systems that we use here. Like we're used to it, so it's easy for us, but like the rest of the world's like, what, why? Tens are so much easier to count by. Anyway, the concept here says the base 10 logarithm is called the common logarithm, is written as log x with the base of 10 implied. For example, log base 10 of what equals x. So this means log base 10 of x equals something, right? Which would end up being as an exponential form, 10 to some power equals x. That's what we were dealing with in the warm-up, by the way. So if you see log x, what it means is log base 10x. The 10 is implied. If you see another number there, it's a different base value. As I throw my pen. But anytime it's just log, the base is 10. If there's no other base, the base is 10. So the next thing we're going to be talking about here is that, oh, here's e again. The base e logarithm is called the natural logarithm, is written as lnx. So this is one that might be a good idea just to hit that. So that means that if you take e to some exponent, the answer is x. But we don't usually write this as log base e of x is equal to some number. We write it as lnx instead. But all those three things, they mean the same thing. But there's a different way of writing this that doesn't actually use e, just uses ln for natural logarithm. But those three things are equivalent, just like over here, those three things are equivalent as well. All right. Now you can evaluate common natural logarithms using your calculator. So log of 900 means log base 10 of 900, meaning 10 to what power is equal to 900. That's what we're solving there. But, well, actually, let's think about this. Does anybody have any estimates before they use their calculator? Any estimates here? What's 10 cubed? 1,000. So 10 squared is 100, 10 cubed is 1,000. So this is going to be like 10 to the 2.9-ish, probably. Oh, by the way, it's right there. 2.954242509. Yeah, it's close to 3 because it's almost 1,000 and 10 cubed is 1,000. So that makes sense. The exponent in this particular exponential equation is going to be close to 3. lne, it tells you the answer. It's 1. What that means is, it's right here. lne is basically a log base of e, right? That's what we're talking about? No, it's log base equal to e, ln. So e to what power? Ln e, here we go. Let's see, e to what power equals e? That's what it's asking. Because ln x right here was log base e to the x power. So ln e means log base, not x power, x as the argument. Log e, ln e means log base e with an argument of e. So e to what power equals e? 1, first power. The only way to make something equal itself using an exponent is if the exponent is 1. Okay. The next one says ln of negative 1.87. So that would be, that's log base e with an argument of negative 1.87 equals x, which in exponential form would be e to what power equals negative 1.87. And as we discussed earlier, negative exponents don't make negative numbers. So error or undefined. What's that? E isn't negative because E is like 2.718-ish. That's what we were using the other day for continually compounding interest. Yeah, so E is a number. Yeah, sorry, I should go back and mention that. E was the number we talked about the other day. It was that irrational constant when we were using continually compounding interest. That was like 2.718, so forth. So yeah, E is a number. It's a positive number. It's almost 3. It's like 2.7 something. Can't raise that to a power to make it negative. Negative exponents don't make negative numbers. So undefined or error. All right. So that's what we're dealing with there. So this one right here, you can, by the way, you can just use your calculator. If you go to your calculator, you will notice that on the left side, right next to the 7, it says log, and right underneath that, it says ln. So all you need to do here is type in for A, log of 321. And that should be just a little bit more than 2, maybe 2.2-ish. I don't know. What do we get for that? 2.5, actually. Okay, more than that. All right, 2.5. 2.51, what does it say? 10,000. No, that would be 4 decimal places. So the nearest 10,000th would be 4 decimal places. So that's going to be 2.5065. That is log of 321, because 10 to the 2.5065 power would equal about 321. All right, this next one is saying e to what power equals 1,215. I don't know, is that like somewhere around 6 or 7? 7.1, okay. That makes sense. So ln 1215. 7.1025, yeah. E to the 7.1025 is equal to about 1,215. And I keep saying these things over and over because I want you to think of them as exponents as well, like bases with exponents. And if you want to write this, you can say 10 to the 2.5065 is approximately 321. Just to keep in your mind that we are dealing with exponents. That's what this is. This whole thing is dealing with exponents. For B, e to the 7.1025 is approximately 1,215. This one's going to be somewhere in between 0 and -1. Yeah, because if you think about it, like 10 to the -1 is 1/10, which is 0.1. This is a little bit bigger than that, so it's in between 0 and -1. The exponent has to be. So type it in, log of 0.17, and yeah, in between -0 and -1, you get about -0.7696. 7696. 4 decimals, yeah. So that means that 10 to the -0.7696 is approximately 0.17. That's what we're talking about. All right. Any questions so far? Okay. Do logarithms feel terrifying? Okay. Not yet. No, I'm just kidding. What's that? Yeah, I mean, with no calculator, agreed. We could estimate though, like you can kind of ballpark it if you wanted to, but yeah, calculators make this. Could you imagine doing this back in like the 1950s? With none of this. Okay. How about this? For log x or ln x. All right, listen up. So for a common log or for a natural log with values of x in order to be defined, what has to be true of x? Yeah, they have to be or non-zero, right? They can't be less than 0. So let's see, x cannot be less than 0 in order for it to be defined. Cool. Because you can't make a negative number from a positive base with an exponent. It just doesn't work. All right. Ooh, hey, look at that. Equations. Ooh. Interesting. Okay. So we are going to be solving for x. Now we get to take a look here. So remember, 10 is not a coefficient, but it is a base. This is kind of going back to the first page where we're talking about the warm-up. You cannot divide both sides by 10 because 10 is not a coefficient, it is a base. It is increasing by factors of 10. It is not multiplying by 10. It is increasing by factors of 10. So we cannot simply just divide in order to do that. But what we can do is we could say, we can make log base 25, because that's a base value there, right? Like if we applied an exponent to that, 25 to the first power would be the same as log base 25, right? And over here, log base 10 is the common logarithm of an exponent with x minus 1. That is not base x minus 1. That is the common logarithm. It is assumed that the base is 10. Actually, sorry, that doesn't even need to be there. Because what we're saying is 10 to what power? Really what we're asking here is 10 to what power equals 25, right? So that's the question here. So 10 to what power minus 1 equals 25. So we can write it right here. And then if we add 1 to both sides, because that's just a 1 now, that'll give us 1 plus log base 25 is equal to x. Sorry, it's not log base 25. What am I even talking about? It's log of 25. I apologize. I'm a little mixed up today. Not a base. We're dealing with base 10 here. This whole thing is, this is base 10 because the base we have is 10. Sorry. The base we have is 10. So we're just rewriting this as log base 10 with an argument of 25 is equal to the exponent of x minus 1. Sorry. I got backwards on that one. Can we start from the beginning and I can explain it a little bit better? Would that work? Because I did not do a good job of that. Hang on. So first thing I want to do, I want to go over here. I actually just want to flip around this entire equation because I think it'll make more sense if it's the other way. So 10 to the x minus 1 equals 25. So the base value with the exponent is 10. So we don't need a base value other than 10, which is a common base, which means we don't need to write a number. So we're taking log base 10, which is just log, with an argument of 25 is equal to the exponent of x minus 1. So that means we write log 25, the base is 10, it's a common base, we don't write 10, equals the exponent x minus 1. That's how I should have explained it to begin with. I apologize that I messed that up. Does that make more sense? So we're just converting it like we did on the previous pages. I got backwards because I was looking at this reversed. So I like to write it over here. Like my variables on the left. I always like my variables on the left. Okay. So here we are with that. And so what we need to do now is just add 1 to both sides. So if we add 1 to both sides, that's going to be 1 plus log 25 equals x. So basically, if you think about like, what do you have to raise 10 to in order to equal it to 25, whatever that is, add 1 to it. So it's going to be 1 point something plus 1. So the answer is going to be 2 point something, right? So if we take 1 and we add log 25, it should be 2 point something, which is 2.3979. And this one just says nearest thousandth. So we'll go with 3 decimal places. So x is going to equal 2.398. So x equals 2.398, or we should go with the approximate symbol because that is an estimation. All right. I hope I didn't make that worse by screwing it up at first. Okay. So that's our first example with equation solving. So let's try another one. Let's try our natural log this time. So we have ln, and that's going to be of 2x to the third power is equal to 4. So basically, we're trying to figure out what this is looking like when we introduce e. So this would be, so that's log base e. So we're talking about a base e to the 4th power is equal to the argument of 2x plus 3. Okay? Exponent here, argument here, e is our base. So we can write 2x plus 3 equals e to the power 4. Or you could write e to the power 4 equals 2x plus 3. But anytime you have ln, that's the natural log, the base value will be e. The value that it's equal to across the way, written in natural logarithmic form, is the exponent. This is the argument. So we're going to convert to that. Are there any questions about that before we solve this? Okay. Now your book expands e to the 4th power as a decimal first. I would not recommend that. I would rather just subtract 3 first and leave e as e. Kind of like, did you ever work in geometry where you answered in terms of pi, where you never converted pi to 3.14? You remember doing that? That's basically what we're doing right now with e. Leave it as e until the end of the problem. I don't know why sometimes people, the earlier in a problem you estimate, the further off you're going to be from the exact value by the end. So let's wait till the end. So let's subtract 3 from both sides. So that'll be 2x equals e to the 4th power minus 3. Which means we would then divide both sides by 2. And so that's x is going to equal e to the 4th power minus 3 over 2. I would just say, open up a fraction on your calculator and type that whole thing in. It's going to be a lot more accurate than converting first into a decimal. So wait until the end to make an estimation. So here we go. We've got ourselves e to the power of 4 minus 3 over 2. And we should be looking at 25.799 for our answer. So 25.799. There's our example, answer for example 5 for that one. All right. Let's keep going. There's a couple more down here. Any questions on those two? Okay. So here we go. Log 3x minus 2 equals 2. What's our base value? 10's our base value. Good. What's our exponent? 2 equals the argument 3x minus 2. You can finish that one on your own. Go for it. Square 10, solve for x. Some of them you don't even need your calculator for. What was that? You're throwing metal back there? Are we watching a video of somebody throwing metal back there? What's going on? What does x equal? Exactly? Cool. Nice. If you were rounding to the nearest 10,000th, then you would have 0.0000. But we don't care about that because we don't need to round because it's exact. All right, 34. Nice. Question for the next one. How are we going to rewrite this one in natural logarithmic form? ln 8 equals x plus 2. So in natural logarithmic form, we've got ln 8 equals x plus 2. Anytime you have the natural log, you don't need to do log base e. You can just write ln equals the argument of 8. Sorry, not equals, times the argument, or not times, but ln of the argument of 8 is equal to the exponent x plus 2. What's our next step? What do you think we should do now to get x by itself? Subtract 2. Good. So x is going to equal ln 8 minus 2. Before you type this into your calculator, let's think about this for a second. E is 2.718-ish. So it's more than 2. And if you think about an exponent of 3 with a base of 2, that's going to be equal to 8. So that means that the sum of these two need to be less than 3. So I'm thinking that x is going to be a decimal somewhere in between 0 and 1. Is that true? Is x a decimal in between 0 and 1? Can't be negative. And if it equals 1, then e to the third power would be more than 8. So it's got to be somewhere in between 0 and 1. So what is it? ln 8 minus 2. ln is right before log. So ln 8 minus 2. Make sure you close the parentheses after the 8 before you subtract 2. What do you get? Yeah, so a decimal in between 0 and 1. There we go. And this one is to the nearest 10,000, so we're actually going 4 decimal places. So that's going to be x is approximately 0.0794. Cool. Oh, no, it doesn't say 10,000. It just says 1,000. Sorry. 1,000. 0.079. Great. How are we feeling about converting between exponential form and logarithmic form? Decent-ish. Okay. Last page. Almost there. Okay. This one uses the metric system. So, using logarithms to solve problems. The seismic energy X in joules, which is a measurement of energy, I think, can be estimated based on the magnitude M of an earthquake by the formula X equals 10 to the 1.5 M plus 12. What is the magnitude of an earthquake with seismic energy of 4.2 times 10 to the 20th joules? So, seismic energy is X. In this case, here's our equation. We good?
Oh.
Okay. Oh, that's not good. You all right? Okay. X is on the left here. X is seismic energy. Seismic energy is 4.2 times 10 to the 20. So it's saying just substitute, which it did for us here. It's just showing us, okay, replace X with 4.2 times 10 to the 20. Then we're going to solve the equation for M. So we have to rewrite this in logarithmic form. And once again, I'm going to just flip around the entire equation, just so I have my base value with the exponent on the left. And then the argument's going to be on the right. So we're going to have 10 to the 1.5 M plus 12 equals 4.2 times 10 to the power of 20. And this is written in scientific notation. So if a problem starts in scientific notation, let's try to keep it there unless the number is small enough to write as a regular number. So if we were to rewrite this in logarithmic form, what's it going to look like? Correct.
2 times 10 to the 20.
Yep.
And parentheses. Am I going to continue?
Yeah, equals.
Okay, equals the 15M plus 12.
Yeah, 1.5 M. Yeah. Yep. 1.5 M plus 12 equals the exponent. Nice. So there's that. So now we solve. What's our next step? Subtract 12. Okay. So we're going to get log 4.2 times 10 to the 20th minus 12 equals 1.5 M. What do we do now to get M by itself? Divide by 1.5. So M is going to equal the log, common log, base 10, of 4.2 times 10 to the 20th divided by, minus 12 divided by 1.5. And that can all just be typed in on a fraction in your calculator, and then you can get your answers. So let's do that. Math,
We went to 1,000.
fraction. What does it say?
I don't think it's-
It doesn't say. Basically, well, we're trying to find the magnitude, right? Looking over here. So I'm going to say, let's go with 1 decimal place because that's what the chart over here uses. And most of the time, and actually, if you think about it, most of the time when you hear about earthquakes, how many decimals do they go to when you hear about an earthquake? Usually just 1. Like it was like a 9.4 on the Richter scale, which is an incredibly high one, but 2.7 off the coast of Oregon, you know? So they don't usually go more than 1 in reporting and things like that. So let's stick to 1. And that's what we have over here as well. And it didn't tell us over here. So we'll just interpret based on what we read here, which is 1 decimal place. So here's our fraction. Log 4.2 times 10 to the power of 20. Close the parentheses, subtract 12, divide by 1.5. That's about a 5.7 magnitude earthquake. So M is approximately 5.7. There we go. 5.7 magnitude. Boom, yeah, cool. Not too bad, right? Like once you get the flow of like switching between the 2 forms, not bad. It's okay. You can do this. All right. Do that one on your own, then we're done. use the same formula from above. This is X now. Same formula from above, but now that's X. And if you want to make it really easy, it's the same thing as before. You're just going to replace this with X, so you don't have to solve it again. Just a little hint there. Because it's all going to reduce to that, so just swap it out. Yeah, because you've already solved for M. That process won't change. So you'd still convert to log base 10, you'd still subtract 12, you'd still divide by 1.5. So the only thing that's changing is what's in the parentheses. And to make it even easier on yourself, you don't even have to type the entire thing back into your calculator. You can just copy and paste the previous one. Scroll back. And just change the exponent to 23. Change the 4.2 to 1.8. That is the only difference. So what's the magnitude? 7.5. Cool. M, that was roughly a 7.5 magnitude earthquake. Great. There's a quick recap down here. So if you want to go back and just like quickly refresh on a couple things in terms of how to convert back and forth between log and exponential form, you can do that there. That's it for today's notes. We got through it. Nice.